Power, average power. So power, P sub AV, average power equals your volts maximum times the current maximum divided by 2 times the cosine of theta. Cosine theta is something called the power factor, which we'll get into in the next card. So your power in watts equals your max voltage, which is where it peaks, times your max current, where your current peaks, and then theta. This cosine theta here for your power factor is the angle of the voltage minus the angle of the current, and it's cosine. So it's always going to be a positive value because that's property of the cosine function. And also power equals voltage times current times cosine theta. If you go with the RMS values, then you don't have to divide by 2 if you use RMS. And VRMS is simply the max voltage divided by the square root of 2, which is 1.414, what have you there. So there's RMS to max. RMS is about 0.707. And yeah, 0.707, that's what I mean. But there you go, there's your max power. Power factor. This is R cosine theta. Again, it's the angle of the voltage minus the angle of the current, which will always be positive. It's the magnitude. See the bars? That means no matter what you get when you subtract the angles, just ignore the negative sign. Just always treat it as positive. So voltage angle of the phase angle of voltage, phase angle of current, it's going to give you a value between 0 and 1. Always, always, always. If you have something greater than 1, it means you did something wrong leading up to getting those angles. Go back and double check your math. So cosine of 0 equals 1, which is the highest power factor possible, which you can get with, say, resistors. Cosine of 90 is going to be 0, which is the lowest power factor of inductors and capacitors. It's often used with the average power formula, which is, as we just reviewed, V times I times cosine theta. And, right, just to recap, for omega equals 2 pi times your frequency, which is 6.28 times however many cycles per second your hertz is. Omega sub s is your 1 over the square root of LC is how many radians per second. So if you happen to be dealing with something that requires units in radians per second, then you simply treat omega as 1 over the square root of LC. Remember, radians is that section of a circle that you learn in trigonometry. 2 pi f. Voltages in series resonance circuits here. So we have here a series resonance circuit, voltage source, series resistor, your inductor, and your capacitor. So voltage across the resistor is equal to the voltage source, which is the current through the loop times the series resistor. The voltage across the inductor at resonance is going to be the same as the voltage across the capacitor, but it's the Q factor, which we'll get into here, times the voltage source, which is also equal to the current through the loop, times the inductive reactance at an angle of 90 degrees. Voltage for the capacitor is same as the Q factor times voltage source, or the current times the capacitive reactance at angle negative 90 degrees. Series resonance. When you're dealing with any RLC resonance circuit, for series, you can use these. For parallel, if you have a high Q factor of your coil, meaning greater than 10 Q factor, then if you know both your inductance and your capacitance, then you can simply use, then you can find your resonant frequency with this formula. The frequency equals 1 over 6.28 times the square root of inductance times capacitance. If you know just what frequency you're aiming for and your capacitance, because let's say you've matched your capacitance to your transformer if you're building a Tesla coil, then L, your inductance, is the reciprocal of 4 pi squared times your frequency squared times your capacitance. Because you see, if we are to put, if we want to get the L out of this formula, then we would just square everything here and just square both sides. That's why frequency moves over here. Then you get frequency squared. That's why you get 2 squared is 4, and there's pi squared. But C remains as square root of C squared is just C. So there you go. And likewise, if you now can easily swap out C over to here, and your L comes down over here, you can just say, if you have a known inductance and you know your frequency, you can tell what kind of capacitor you want to get. If you know the inductance of your secondary coil in your Tesla coil, and you want to know what kind of capacitance or top load to use, you can use this formula. And you would want to have that to be the same frequency that your tank circuit of the primary is operating at. So there's a helpful little tip that I kind of figured out on my own.